So when we talk about box plot shapes, we got to be a little careful because it can be a little tricky. I will tell you this. You cannot tell how many modes there are. You can't tell if it's uni or bimodal. Okay, so you can't tell that. The only thing that a box plot can help you see is the skewness or whether or not it is symmetric. So cannot tell modes, but you can tell symmetry or skew. So if you think about your median being right here in the middle, you think about your median being right where the line is for the box. Remember, median is pretty close to the mode. Sometimes it's just slightly off if it's skewed, but it's pretty close to the mode. So if you think about that, like here's probably ish where the peak is, and then just think about connecting that to the ends of the whisker. Now you can kind of see it. What is the shape of this distribution? This would be a left skew. Yep, skewed left, left skew, same thing. All right, if I talk about this one, top right, again, think about that the mode would be kind of right about there, pretty close to the median. And then if I go out to the ends, that one is approximately symmetric, I would say. Class 2 on that graph. This one is... That one's right there on the slightly left skew, kind of right there on the edge. That one, if you said was approximately symmetric, I'd probably give you full credit for it. If you said it was left skew, I'd probably give you full credit for it. If you said it was right skewed, we might have to talk, okay? But that one is right there on the edge. These ones on the bottom here. The one for the award-winning actresses, the one with all the outliers. So, again, right. What do you think about that one? Pretty right skewed. I would definitely say that has a right skew to it. Now, looking at this one that looks like it fell over, what do you guys think? What do you think about the shape on that one? Skewed right, skewed left. Okay, remember, you always have to go from lowest number to highest number when you're talking about shape. So we would want to look at this with our head tilted to the left, or think about taking your paper and turning it from lowest to highest, left to right. So this would definitely be a right skew. Okay?
There's a lot going on.
All right, looking at the one on the bottom here, there is a lot. There's 5 boxes. Now, again, make sure you're going from lowest to highest number. So make sure you're thinking about this, tilting this the correct way. So the first one on the far left, the graphic novel, what do you guys think? That one's approximately symmetric, I would agree. How about humor? Left skew, I would agree. Graphic memoir. Yeah, it's got a little bit of a right skew, yep. And then nonfiction, approximately symmetric. And then graphic fantasy, left skew. Cool. Do you guys have any questions on that?
No.
Perfect. Again, don't ever tell me that it's uni or bimodal because you don't know that. Okay? You can only tell skewness or symmetry. All right, let's do standard deviation. Are you ready? Let's do it. All right, you guys, what time would I be at school if I said that I will be at school within 5 minutes of 7 a.m.? All right, this is going to be somewhere between 6:55 a.m. to 7:05 a.m. Okay? Now, I could also say the same exact thing by saying I will be there at 7 a.m., give or take 5 minutes. I'm saying the same thing there, okay? So does that mean that I will never get here at 6:50? Does that mean I'll never get here at 7:15? Not necessarily. It just means, on average, on a typical day, I'm going to be here between 6:55 and 7:05, and that is what is normal for me. If I'm here a little bit before or after that, that doesn't mean that the world has fallen apart, but it's just outside of my normal time, okay? Could I even get here right at 7? Sure I could. Sometimes I'm going to get here right at 7. That little give and take, that little 5 minutes window basically, that is kind of what standard deviation tells us. It tells us on average how far we deviate from the true mean of a distribution. So standard deviation measures the average distance from the mean. Standard deviation is the average distance from the mean. It's literally an average. Standard deviation is an average, and it is the average deviation from the middle of a distribution, the mean of that particular distribution. So here's kind of the way that you find standard deviation. Now, this is the lazy person's way, okay? But this is the general idea. So here's our data set that is so loved. 1, 2, 3, 4, 5. What is the mean? The first thing you do is you find the mean of the distribution. What's the mean of this distribution?
3.
It's 3. So my x bar, my mean of this distribution is 3. And what I need to do is I need to find the average distance of each data value from that mean. So how far, what's the distance from 3 to 1? That has a distance of 2. These are my distances. And what's the distance from 3 to 2? 1. Now, here's the one that everyone always forgets. What's the distance from 3 to itself? 0. What's the distance from 3 to 4? 1. And what's the distance from 3 to 5? 2. Again, this is the lazy version of doing standard deviation. I just found the distances. I took the absolute value, basically, of the distances. So instead of getting a negative number here, I went ahead and just talked about the distance. All right, now, if I find the average distance, so now I'm going to average these 5 numbers, these 5 distances. What would be the average of 2, 1, 0, 1, and 2?
1, 1, 2.
Perfect. So the average of those distances is 1.2. So what that says is that, close enough, easy, lazy way, is that this distribution has a mean of 3 and an average deviation, standard deviation, of 1.2. Meaning if I go from 3 and I add 1.2, I would be at 4.2. So that's the upper end of the give or take. And if I go from 3 and I go down 1.2, I would be at 1.8. That's my lower average deviation. And what that tells me now, guys, is that the majority of my data should be within that 1 standard deviation from the mean. And it is. I have 3 out of the 5 numbers is within that 1 standard deviation. So, my data is normally somewhere between 1.8 and 4.2 for this particular distribution. Are there some distances that are bigger than that? Yeah. There are some distances that are smaller than that. But on average, I have a distance of 1.2. Yes, ma'am?
Is every outlier going to be outliers with both the standard deviation?
That is such a great question. Thank you for asking that. Just because I am outside of 1 standard deviation, like the 1 and the 5, I am outside of 1 standard deviation, so I'm outside of what's considered normal, that doesn't automatically make it an outlier. So, outliers are fully based on the 1.5 IQR rule. Yep, very good. Great question. Now, 1 and 5 are outside of what's considered normal for this distribution. It's outside of the majority, but it's not considered an outlier unless I check that. And we don't have to check it, but that's the idea. So that's the idea behind standard deviation. Now, there is a very complicated mathematical formula for standard deviation. This, again, is like the lazy man's way, okay? So I'm going to show you guys the actual formula. Please try not to, run screaming from the classroom. But here it is. First of all, the notation for standard deviation is S sub x is how you say that. S sub x, because it's a subscript, S sub x equals, this is the notation for standard deviation, and that equals a big ginormous square root. So one thing you do need to know is that standard deviation is a square rooted number, okay? Every standard deviation has been square rooted. I know we didn't take the square root a second ago, but again, that was the lazy man's way. You do the summation, so that's that sigma guy, of x sub I, so that's each x value, minus the mean, x bar, squared, divided by n minus 1. So this is the non-lazy version of standard deviation. Basically, what you do is you find the mean of the distribution, just like we did a second ago. You find out how far it is from each individual number. Now, you take the number in the distribution and subtract the mean. So 1 minus 3 would give me a negative number. Hence, then, why I have to square these numbers, because I can't have a negative in a distance. So I square all those distances, or all of those subtractions, and then I add all those up. I divide by n minus 1, so the number of numbers in the distribution minus 1, and then once I do that, I take the square root to bring them back down to the actual value. So that's how you find standard deviation formula-wise, the non-lazy person's way. If you're in AP Bio, you've already been doing this, and you've written out you found all the means, and you did all of the subtractions, and you squared everything. You probably made a table and all that fun stuff, and you added all this stuff up, and great times, right? How do we in AP Stats find standard deviation for real? We're going to use our calculator. Use the calculator, ladies and gentlemen. The reason for that is because in the real world, in real statistics, ain't nobody doing standard deviation by hand.
Thank you.
We don't do standard deviation by hand. So sorry. So we're going to use our calculator, because if we have tools to use, we might as well use them. So here's what we're going to do. We're going to input data into L1. So we already did that last week. We learned how to put that data into L1. For a reminder, that is stat edit. Stat edit. You'll put that data into L1. After that, we already did this last week again. We're just doing it and focusing on a different value. You go to stat calc 1 for one variable stat. And you are basically then looking for the SX number. I believe it's the fourth line down. And that is going to be your standard deviation. In statistics, we are most interested in the interpretation of standard deviation. So we'll talk about what it actually means here in a second. We've already talked about it, but I'll tell you how to interpret it here in just a second. So this is how we're going to calculate standard deviation. Yes, there's a formula, but the biggest thing you need to know in regards to the formula is that standard deviation is a square rooted value, and that will help us later in chapter 5. So I'll remind you then. All right. So let's think about this for a second. Do you think that standard deviation is resistant? Is standard deviation resistant? First of all, remind me what resistant means.
It doesn't change.
Yeah, if something's resistant, it means it doesn't change when extreme values change. Do you think that standard deviation is resistant?
No.
Why not?
It's a median. No, it's a mean. It's an average.
Very good. Very good. Standard deviation is not resistant. It is an average distance, and means are not resistant. If I go and change my numbers 1, 2, 3, 4, 5, if I change that to 1, 2, 3, 4, 50, I've got a really big distance that now I have to average in, and that's going to change my average for my distances. So standard deviation is very not resistant. It's also based on a non-resistant mean. The mean is in the formula, right? So like I'm taking an average and using an average within that formula. It's very not resistant. All right, some important properties of standard deviation. All S sub x standard deviation values, all standard deviations must be greater than or equal to 0. Why can't standard deviation be negative?
No negative distance.
I can't have a negative distance from the mean. I can't be like negative 10 distance. That would be weird. Now, can the standard deviation be 0?
Yes, yeah.
How?
It'd have to be like it always happens a certain way every single time.
How would it be that I would have a set of data that has an average distance of 0? If all of the numbers are the same number. 10, 10, 10, 10, 10. What is the distance from the average of 10 to itself, 10, every time? 0. And if I add all those up and divide by anything, I still get 0. So you will get a standard deviation of 0 if all of the numbers are the same in the distribution. Okay. Another thing about standard deviation. Large SX values indicate a large spread in the data. The larger the standard deviation, the further we had to go to get those distances. So I'm going to draw you guys a few examples of some graphs. My bars are not the same width. I'm so sorry. I'm violating the area principle as we speak. I know, for shame, for shame, for shame. All right, there are my graphs. Do you guys see where the mean is for each of the graphs? Where's the mean? Literally the middle of every graph, right? So here would be the mean, here would be the mean, here would be the mean, and this would be the mean. So there's the mean for each of those graphs. Now, average distance from the mean. What is the distance from the mean for the majority of this data? Like 0, right? Like right on it, right? Then I have to go out just a little bit, a couple of times. Remember, the height of the bar is how frequent the values occur. So I am frequently going not far from my mean, and then a few times I have to go out. Here, what's happening? I'm having to go out more frequently than staying close to the mean. So which one of these has a bigger standard deviation? Yeah, this one's going to have a bigger standard deviation because it's having to go out from the mean more often than staying close to the mean. So I'm averaging a distance that's more than 0 often. Looking at this one, I am staying close to the mean most of the time, but there are some times where I have to go further out than this one. So this one would have an even bigger standard deviation than this one. And then this guy, I'm having to go a far distance very often in both directions. This one has the biggest standard deviation. Make sense? So these are in order from smallest standard deviation to largest standard deviation. Any questions on standard deviation and what it might look like on a graph?
Nuh-uh.
Cool, cool? All right. Let's do a calculation then. And then we can interpret. So, a random sample of 5 students was asked how many minutes they spent doing homework the previous night. Here are the responses in minutes. 0 minutes, 25 minutes, 50 minutes, 60 minutes, and 90 minutes. Where are you guys in that? You did 0 minutes last night? What did you say? Significantly above that? Wow. You guys must be an A-push. All right. We are going to calculate and interpret the mean and the standard deviation. We are going to calculate and interpret the mean and the standard deviation. So, I do not want you guys to calculate the mean by adding those 5 numbers and dividing by 5. Don't do that. Why not? You already know you got to get the mean and the standard deviation, so you might as well get them both at the same time using the list in your calculator. So get used to using the L1, the stat edit. So I will show you guys on the screen if I can get there. So if you go to your calculator, for those of you who don't have your calculator with you today, you can kind of watch and see it happen on the screen here. So you go to Stat, you hit Enter on Edit, and you put your data into L1. You do need the 0 because the 0 is one of the data values. Okay, make sure you have the 0. So we did Stat Edit, and we put our data in. Where do we go now to make our calculator calculate the stuff? Stat, hit the right arrow to calc, and this is one variable, so we're going to go to the one variable stats. My data is in L1. I'm not changing the frequency of anything, so everything's just used one time, and then I hit calculate. And at the very top, we see our mean. What is our mean? X bar, that's the 45. And which one is our standard deviation? S sub x, 34.28. 2 decimal places is usually acceptable. Okay, 2 decimal places. I'll tell you when you need more than that. 2 decimal places for now. So 34.28, and we do round, we don't truncate. I don't know if some of you do that, but we round, regular round. All right, so back to our question. So we have a mean of 45, so our X bar was 45. And we had a standard deviation of 34.28. Alrighty, so to interpret. Interpret means basically write a sentence saying what this means. This is the most important part of what you need to know how to do for standard deviation, is recognizing when you have a big standard deviation, a small standard deviation, and what the standard deviation means. So, what does it mean? Well, these kids, on average, spent 45 minutes doing homework, give or take 34.28 minutes-ish. Okay? So, that's like the general, what people would say. We can say kind of a very similar thing. These students spent 45 minutes on average on homework. This typically varies by 34.28 minutes. So that's my typical variance. That's my typical give or take. So what that tells me is this. Now this is just me trying to help. So at this point, that's answering the question. This is now just me trying to help you fully understand and grasp this. On average, these kids spent 45 minutes. Give or take about 34 minutes. So these kids spent somewhere between 11 minutes and 79 minutes on their homework. The majority of these kids will be somewhere between there. And they are. 3 of them are between 11 minutes and 79 minutes. There are two that are a little bit outside the norm, which should make sense. Because if I have an average distance of 34, some have to be more than that, some have to be less than that. Okay? So if you call up a friend that's part of this group and you say, hey, how long did it take you to do your homework? And they say, I didn't do any homework. Is that outside of what's normal for these kids?
Yes.
Yeah, a little bit outside of what's normal. Okay? Are they an outlier? I don't know. I'd have to do the 1.5 IQR rule to see for sure. But what if you talk to one of these friends and they say, hey, I spent 65 minutes doing my homework. Are they outside of normal?
No.
No, that's pretty typical for them. Okay? Make sense?
Yeah.
Perfect. There's standard deviation and what it means. All right, now here's the fun part. What happens when I start changing things? Let's think about these same numbers. 0, what were they? 0, 25? 50, 60, and 90. Let's say we take out the kid who spent 90 minutes from the data. What's going to happen to the mean of 45? It's going to decrease because I'm taking out a really big number, and so my mean is going to decrease, okay? The mean will decrease. What's going to happen to the standard deviation?
Also decrease.
Why is it also going to decrease, Danny?
Oh, it's decreasing because the bigger number is gone.
Good. So the distance from 45 to 90 was 45. And that is a big distance. It was bigger than my standard deviation of 34. So if I take out a bigger number, just like it did with the mean here, it's going to decrease my standard deviation as well. So the standard deviation, will also decrease. Okay, I have one more question for you that's not on your page. Let's say that we have these same numbers. Okay, remember my mean was right here at 45, and my standard deviation from that went out. That's not equal, but whatever. There was my standard deviation, okay? What happens to the mean if I take out the 25? What would happen to the mean of 45 if I take out the 25? It would go up. Very good. What happens to the standard deviation when I take out the 25? It does not stay the same. It will actually increase a little bit. Okay? Because I'm taking out a number that is inside of the standard deviation. So I'm taking out a number that was smaller than the average deviation. And so this 45 is going to go up, which is going to make this distance to 0 bigger. Okay? And so that is going to, and I'm taking out a smaller distance. So basically, if you take out a number that's within the standard deviation, if I took out the 25, the 50, or the 60, my standard deviation would go down. Would go out. But if I take out the number that's outside of the standard deviation, my standard deviation comes in. Okay? That's how standard deviation works. Questions? All right.
I have a question.
Yes.
So if the mean goes down, standard deviation goes down.
Not always. It depends on where it's at. So just because if the mean goes down, that doesn't automatically mean standard deviation goes down. It just depends on where the value is that you took out. Just depends on where it is. All right, I do want to do a quick little summary here. You are welcome to write this down if you want, or you don't have to. It's your choice. But when do I use which thing? If I have symmetric data, what measure of center should I use, mean or median?
Median.
Symmetric data, I would actually use the mean. If I have skewed data, I should use the median. Why is that?
Because this
It's
is
closer to the
than
dollar.
we mean.
So my skewed data is going to mess with the mean. The mean's going to go toward the skew, okay? Remember those dots that I put on the board, right? And when I started putting dots further out, the mean started coming toward the skew. And so if I have skewed data, if I'm trying to find the center, like a good representation of the center of the data, I should probably go with the median because it is not going to be as swayed as the mean is. So if I have symmetric data, I can just go with the mean, which is the most common one. Which measure of variability does the mean go with? So sometimes range, that one can kind of go either way. So the one that always usually goes with the mean is this standard deviation that we just learned about. Standard deviation and mean are pretty common to go together because the standard deviation is based on the mean. What measure of spread or measure of variability is very common to go with the median? Yeah, that's your IQR. And the reason behind this is that the mean and the standard deviation are pretty good in the symmetric world because of the fact that they are not resistant. But the median and the IQR work just fine for the skewed data because they are resistant.